Our speaker today is Rafael Reyes. He did his PhD from the Institute of Space and Planetary Astrophysics at the University of Karachi, Pakistan. He started a postdoc at the Department of Astronomy, University of Concepcion, Chile in 2016 on a German-Chile CONICET project. And now he's working with the same group with an independent FONDICET postdoc fellowship since 2019. So Rafael is going to talk today about fragmentation and mass accretion affecting the stellar IMF. Okay, you can begin, Rafael.
Okay, thanks for the introduction and welcome you all. Since I'm going to talk about the stellar IMF in the context of fragmentation and mass accretion, so perhaps we need to go into some background as well in terms of the star formation history. But before I do this, these are my collaborators, Dominik Schleicher and Siegfried van der Verbeek, Ralph Klessen. I work with these people. So let's have a quick cosmic history in terms of the star formation. The cosmological simulations, the lambda CDM models have suggested that the molecular hydrogen was inside the mini dark matter halos, and it was collapsing, providing the cooling which is actually required to collapse the gas. And when this was happening, the H2 was enabling the gas to drop down from 1000 Kelvin to just 200 Kelvin. And so the star formation requires the cooling. So the cooling was provided by the H2, which was present there. And this was happening just after 200 million years from the Big Bang. And but still, if you see the temperature, it's 200 Kelvin. It's relatively high as compared to what we observe in today's star-forming regions, where the temperature ranges around 10 Kelvin. So this relatively high temperature is actually an indication that the mass of this fragment would be relatively high. And when it starts accreting, growing in mass, it's going to end up with a very massive star. So these first stars, which came into existence inside the dark matter mini halos, were quite massive in general, just because the gene's mass was quite high. And since these stars were quite massive, so they had a very short lifetime, and when they end their life, they actually exploded in terms of supernovae, and that supernovae provide the metal enrichment for the next phase of the stars to form. So the first stars we begin with is actually known as the population 3 stars. We call it Pop III stars. And when these Pop III stars exploded, they provide the metal enrichment, because inside these stars, the new elements were forming. And by the time the supernova occurred, all the heavy elements, they scattered into the atmosphere. And the next phase of a star formation was happening with a relatively enriched material, rather than just from the H2 and the helium. So the next phase of a star formation is actually the population 2 stars, which we expect that these stars are not that massive as compared to the very first stars, because now they were forming with some enriched materials, for instance, carbon, nitrogen, and oxygen. And it is also important that we call it metal line cooling agents. So these metal line cooling agents actually providing the cooling in the star forming gas, and the temperature was dropping fairly significantly. I mean, much below than 200 Kelvin. And that actually affects the gene's mass, which is the mass of the fragment with which you start in terms of the star formation and the mass growth. So these metals available for the next phase of the star formation actually provided efficient cooling, and the gene's mass was dropping down. And then we proceed further. When these stars exploded, they provide even further enriched material for the environment. where the star formation can occur. And so the Pop I stars, which are the present stars categories, these are in fact fairly low in terms of the masses with which they form when we compare the population 3 stars and the population 2 stars and the population 1 stars. So this is the overall picture, which actually gives you the idea that the metal enrichment was progressively going on from the first generation of stars to the last generation of stars, which is the present generation of stars. And along with these metal cooling agents, the dust was also created within the supernova explosion. So the dust was also one of the major ingredients which can provide the cooling. So cooling remains fairly important because it helps the gas to collapse to form stars. So this overall picture gives us the idea that H2 actually provided the first generation of stars to come into existence. Then later on, the metals were forming and they were present in these star forming regions, and they were providing the cooling, and then also the dust, which is providing the efficient cooling mechanism. However, it is also important to notice that at what densities of the gas these agents actually start playing their role. So when we talk about the metal line cooling, we see that it is around 10 to 2, number density 10 to 2 per cubic centimeter. At this density, we expect that the metal line cooling is going to play its role and provide the cooling in the gas. But the dust, which is an efficient cooling mechanism, that dust actually plays its role at relatively higher density, 10 to 6 per cubic centimeter. So with this overall picture, perhaps we can move forward. So what we have seen is that perhaps the H2 and the HD, these agents could provide the cooling. And then the gas metallicities can also provide the cooling and let the star formation to occur. And then we also see the dust is present later on, and that actually provides the cooling, and the star formation is actually happening in a more efficient way. But the question is this the entire picture when it comes to the star formation and the masses of the stars that we are going to address? It seems that there are certain things which are still missing. For instance, we must need to take into account that the CMB radiation history is also very important. Why? Because it is the CMB can actually provide the minimum temperature for the gas to begin with in terms of the star formation. So if the CMB is providing the regulation in the gas environment to form the stars, it's going to play its role, because it's even in the presence of dust and the metal agents, the CMB can actually affect the overall temperature of the star and actually can control in some sense how the stars are going to form and with what masses they are going to form. So the CMB is important to be considered. And also we see that if we talk about the CMB, we also need to take into account another aspect as well, which is still missing, and that is the cosmic rays role when they provide the ionization in the star forming gas, and that can actually affect the star formation process itself. The cosmic rays has the ability to permeate into the deepest part or the densest part of these star forming regions and can actually affect the temperature. So this seems to have, well, it could, maybe it is not the entire picture, but it covers quite a lot in terms of the star formation and what are the agents that can actually play their role in terms of affecting the process of the star formation. This slide, I especially consider this slide a very important one in terms of explaining how the star formation occurs, and also the stellar masses as well, which will be discussed in the IMF concept. So what you are observing here is the thermodynamical evolution of a collapsing cloud. the temperature with respect to the number density. And all these curves are actually representing specific metal contents. For instance, over here, this is the curve which represents the present day star formation, where you can expect that the temperature is around 10 or slightly below 10 Kelvin. So how the evolution going on in terms of the density, the evolution of the density and the temperature. So what we see, if we compare the two extreme cases, this is the present day star formation case, where the metallicity is fairly high. And over here at the top, you observe another curve, which is a solid line, which actually represents the primordial star formation, where the metals are not there, the dust is almost not there. So you expect that the evolution, the thermodynamical evolution is happening in a sense that the temperature is actually not really dropping down below around 200 Kelvin, as I discussed previously, that the first stars were actually because of the molecular hydrogen, and that was actually dropping the temperature down to just 200 Kelvin around. So this picture actually gives you the idea that how, with respect to the variation in metallicities of the gas, affect the thermodynamical evolution of the gas. Thermodynamical evolution is quite important, again, when it comes to the star formation. For instance, if you consider the evolution, we see that the density starts increasing as the gas collapses. So let's picture that there is a sphere of gas collapsing under the influence of certain cooling agents available. So initially, the density of the gas is a bit low. So all the energy which is converted from gravitational potential energy to the heat energy, that energy can actually leave the system quite efficiently. And the temperature of the gas or the temperature of the sphere remains almost the same. We call this particular phase of collapse the isothermal phase of collapse. And this isothermal phase of collapse continues to a certain density value. And it is this particular density value which actually determines that the opacity is low and the radiation can actually leave the system quite easily. But it's not always the case. There comes a point in terms of the collapse that the density is high enough, which can offer the opacity high enough, which can start trapping the radiation inside the gas. So now when the density is quite high and the gas is trying to collapse, well, the phase is no longer the isothermal phase. It now becomes the adiabatic phase, just because the opacity of the medium is getting higher and it is starting the heating to be trapped inside the gas. So the thermodynamical evolution can actually be considered in two phases. The first is the isothermal phase, and then comes the adiabatic phase of collapse. So what you are observing in this diagram is a red line, which actually representing the idea that by this time, the opacity is high enough and the gas beyond this red line is now in the phase of adiabatic collapse. Before that, this is the phase of isothermal collapse. And also, if you notice that these are the masses, the gas, the sphere masses, and these are actually the Jeans masses. So what you see is that if you talk about the present day star formation with high metal contents, you see that the temperature is around 10 Kelvin. And in the presence of high metal contents, the temperatures can even drop down below 10 Kelvin, but it almost march forward in time as if it's the isothermal phase is going on. As we discussed that the initial lower density cases, the thermal evolution could be isothermal. So, but this, by the time that we reach to this red line, we see that the temperature starts increasing. It's no longer isothermal. And then you are entering into the adiabatic phase of collapse. It is also important to just mention these important features. in the first phase, the line cooling is playing its role. In my first slide, I represented the idea that the metals are actually playing their role at a lower density. So the metal line cooling is available in this region. And when the gas is getting dense enough, it starts experiencing another phase of cooling, which is the dust cooling. It kicks in at a higher density level. But both with these metal line cooling and dust cooling, as the evolution marches forward in time and reaches to the adiabatic phase, then comes the case that the evolution is almost universal. I mean, beyond this, before this red line, you can see that different metallicities follow different evolutionary trends. But once they find themselves in the adiabatic phase of collapse, the trend is almost universal. It's really hard to determine which path is actually belongs to which metal content. So the universal trend is in the adiabatic phase. But before that, it's actually possible to determine what kind of metal contents are there. One more point, which is also important, that this study, which is provided by Umukai 2005, they considered the CMB contribution, the present day CMB contribution, and that's how they model the evolution. It's a one-dimensional model, by the way. So they model this evolution, how the collapse going on and how the thermodynamics of the collapsing cloud actually happens. However, with this in mind, perhaps we can ask this question: that does this actually affect the IMF itself? So before I go into the IMF, let's have a very quick introduction to the IMF. We all know that the star formation occurs in form of clusters. Stars do not form in isolation. So whenever a population, a newborn stellar population come into existence, it comes with variety of masses of stars. So the observations have suggested that the high mass stars, they are low in number. Over here you find the number of stars, and along this x-axis you have the masses of the stars. So whenever a new born stellar population is observed, we find certain trends that high mass stars are relatively low in number. And when you start moving towards low mass stars, you find that the numbers starts increasing. And once you find yourself in the regime of low mass stars, or for instance, the brown dwarf regimes, then we see that different approaches starts giving us different results. That there's hardly any consistency in terms of the approaches adopted to determine what kind of masses are there in the given stellar population. I'll discuss this why it is so, but this is just a general idea that whenever the star formation occurs, it occurs in form of burst. The cluster of stars having variety of stellar masses, and when we analyze these masses, we come to know that there is a trend, and this trend is known as the IMF, which suggests that the lower masses are relatively higher in number, and high mass stars are relatively low in number in any given population. So with this picture in mind, let's ask again a question: that does the CMB, which is, as I mentioned before, that the CMB can actually regulate the temperature. And it is important why the temperature is so essential to be considered, because it is the temperature which sets the gene's mass and hence sets the minimum stellar mass. Obviously, it grows in time, but with which you start plays an important role in terms of with which you end up the stars in terms of the mass. So CMB, can the CMB play any significant role? This is the question. So in order to address this question, we have to see quickly the history of the star formation process. If you go back in time, you see that you expect that the CMB radiation must be higher in terms of its temperature. So if you cover the range of redshift from 2.7 to around 17, we find that the radiation temperature, the CMB radiation temperature is going to be much higher. What are the values? I'll discuss this in specific sense, but just to give you the idea that at present, the CMB is just 2.7 Kelvin. But if you go back in time, when the universe was quite young, you expect that the CMB temperature was fairly high. And this high temperature is going to set a very high Jeans mass. And that means that the minimum mass of the stars or the fragments could be higher. Over here on the left, you again see the IMF trend. We see this green region represents that there is quite a consistency available when we follow different approaches in terms of defining the masses of the stellar population. The high mass range of the stellar population, more or less every single attempt made to understand the higher masses of the stellar population, we see that there is quite a good agreement. But when you talk about the lower masses, we see that the different results coming into play. I mean, people reporting different masses for the low mass objects in a given stellar population. And there are certain reasons why, because these low star cases, we expect that there are more embedded cases. These stars, these low mass stars are embedded stars. It's hard to see them. So different approaches may come up with different results. So over here, we find some convergence. Over here, it's not there. The convergence is not there. By the way, when we talk about the IMF, it's also, well, we all know that IMF is the empirical function. But when we talk about the cosmic history, and when we talk about the first stars, obviously there are no evidence. We don't have, we cannot see back in time and observe these stars, what kind of masses were there. But so in order to talk about the IMF for the first stars, first generation of stars, we have to rely on computer simulations. So let me go back. What you're observing here is the low mass end, and I'm still trying to address the first generation of stars. Well, I already mentioned that these first generation of stars were quite massive, but still, we need to consider this low mass end for the IMF for the first generation of stars, and I'm going to give you the reason why it is so. So there are studies available. For instance, Clark 2011 have performed the simulations, and they suggested that although the general impression is that the first stars were very massive, just because the high Jeans mass. But if you consider the evolution of the gas, and you consider that the disk is going to form eventually in a rotating sphere of gas, even if it's a primordial gas, you expect that the disk is going to form and it's going to fragment. So this disk fragment is another criterion for the fragmentation, in addition to the Jeans mass criterion. And it is very essential to understand the disk instability, which actually provides you another level of fragmentation, which could be lower than what you expect from the Jeans mass criterion. So the Clark 2011, they performed simulations, and they came up with the idea that even the primordial stars can form in these disk structures, and they must be quite low in terms of their masses. We also performed in 2018 the primordial study, and we also form a disk structure which is going to eventually fragment, and we end up with masses quite small as compared to the first impression that we were getting when the simulations were performed at the very beginning. It was around 2000, 2001 when the first simulations were attempted to understand the masses of the first stars. The results were suggesting that there were very massive stars. But then later on, when we bring more physics into the models, we come to know that actually low mass stars can even form in the primordial environment as well, just because of the disk instability. So we also we know that there is a Toomre Q parameter which actually plays an important role in terms of understanding the disk instability, which can give rise to the fragmentation inside the disk. So whenever the Q goes below 1, we expect that the fragmentation is going to occur. So this criterion going down 1 in terms of the Q value is actually dependent on the sound speed, which is representing the thermal state of the gas, and it also represents the surface density of the disk as well. So this Q parameter is dependent on the thermal state of the disk and also the surface density of the disk as well. So if the disk is high enough in terms of the surface density, there is a good chance that the Q will drop down and the disk will start fragmenting. I would also discuss this in a sense that the disk instability is a linear process, while when the fragmentation occurs, it actually is a non-linear process. Now, people discuss the non-linearity or the linearity in all possible ways, but what I want to say here is a sense of causality. I mean, we all know that cause and the effect, there is a chain. Every effect has some cause behind. So as long as the causality is unidirectional, we say that the process is linear in its nature. For instance, if you have a disk, and if the disk is thick enough, then it going to make the Q drop down below 1, and then this can fragment. So high density, surface density of the gas can make the Q drop down and can cause the fragmentation. But once the fragmentation comes into existence, now this is a non-linear process. Why? Because this fragmentation can actually, when the protostars are formed, they start radiating. And this radiation feedback from the protostars is going to affect the disk environment. And now the disk cannot fragment as it was fragmenting originally in the absence of the stellar feedback. So there is a feedback available here. Cause, effect, and then the effect is actually affecting the cause itself. So now the causality becomes bidirectional. And in that sense, we say that the fragmentation itself is a non-linear process, because now the feedback is involved and it is affecting the disk structure and hence the subsequent fragmentation happening in the disk. So in that sense, we see that the linear and the non-linear processes involved in the disk structure can trigger the fragmentation of different masses. Again, I often work with the primordial star formation, so that's why many of my slides are actually about the primordial stars. For instance, when you talk about the masses of the stars, when you talk about the IMF, at least in a sense that the simulation data suggest what. So there are a lot of attempts being made so far, and we see that from 2000 to 2018 or 20, we see that now people are realizing that even low masses are even possible in the primordial range as well. Otherwise, we started with something of mass around 10 to 100 solar masses, or even, look at this, that's more than 1,000 solar masses could be possible for the primordial gas environment. But now we realize that it is possible to have low mass stars. So even when we talk about the IMF, it makes sense that even the primordial IMF, based on the simulation data, can take into account the low mass end as well. So the low mass end of the primordial star is also important in another aspect. And that aspect is, can we actually detect these low mass stars formed as a first generation, as Pop III stars? Well, the simulations again have suggested that even a zero point 0.8 solar mass object, if it was there, it can survive to the present day. How it is possible that you can have 0 0.8 solar mass object in a primordial environment? We know that when the disk is there, the disk can fragment. And there is one more aspect that perhaps I missed, and that is the ejection of the protostar from the parent cloud or from the disk structure. If it is ejected from the parent structure, it is going to stop accreting. And if it's a star with a 0 0.8 solar masses and it simply ejected from the parent cloud or from the disk, it will no longer accrete. So it can survive quite long. So suggested that 0 0.8 solar mass object, if it was ejected from the parent cloud or from the parent disk, it can survive even today. And people are suggesting that you can find these first generation stars if you look into the Milky Way halo or the dwarf spheroidal galaxies around the Milky Way halo. These are the potential sites where you can find these objects. So far, there are no evidences, but simulations are suggesting that it's worth trying finding out these objects. So far, we have found carbon-enhanced metal-poor stars, but not the pure Pop III stars. We are still building up the background. Again, Clark in 2008, they performed simulations with dust present in the cloud. And they formed the IMF, again, based on the simulation data. And that IMF was peaking below 1 solar mass. Look at this. The IMF, it makes sense now that the low mass end of the IMF, even for the primordial case, is making a lot of sense because the simulation data is pointing out that it is possible to form low mass objects, low mass stars, even in the fairly young universe. But this is mainly due to the dust presence. When the dust is there, it provides the efficient cooling and it can drop down the temperature and it helps the stars to form with very small masses. But the very genuine question is where this dust actually has come from. Well, the dust can come from different sources. For instance, there are papers suggesting that at a redshift of around 8, you expect that the quasars are observed with large dust masses of the order of 10 to 6 solar masses. And there are many papers. I'm just quoting a couple of papers that, again, the quasars are redshift around 8.38. You expect that the dust is there, and that dust can actually provide the efficient cooling mechanism. And the amount of dust can be as high as 10 to 6 solar masses, which is fairly high at that higher redshift environment. So this, from where these dust actually come from, well, we expect that the supernovae, the first generation supernovae and the AGB stars, they can provide the dust, and which eventually play a significant role in terms of the stellar masses that we come up with in terms of the stellar population. So supernovae can provide the dust, the AGB stars can provide the dust, and you can have star formation happening in the presence of gas regulated with certain temperatures. Now I come to my simulations, which we performed more recently, and we published the results. What we do in our simulations is that we have a sphere, and this sphere is in the presence of the CMB radiation. We assume that the CMB is present for this gas sphere, which is going to collapse. So obviously in our simulations, there are certain fundamental assumptions. So some of the assumptions are that the spherical gas cloud is there with molecular hydrogen. The efficient dust cooling is also present in this sphere of gas, which is about to collapse. And obviously, why it is collapsing? Because it is Jean's unstable cloud of gas. So with this, we expect that in the presence of the CMB, this star forming pre-stellar gas cloud is going to collapse. So this is our fundamental setup of the simulations that we performed to understand how the CMB can contribute towards the masses of the stars that came into existence as a result of our simulation experiment. So again, let's have a quick look at how we actually set up our simulations, which will give you the idea what are the initial conditions that we followed in our simulations. Like all simulations, our simulation follows a specific numerical code and a numerical scheme. We call it the smooth particle hydrodynamics technique, and the code itself is called the grade SPH. This code was published in 2009 by Siegfried van der Verbeek, who is one of my collaborators. And since then, we have been using this code quite efficiently. Let's have a quick look what were the initial conditions for the gas sphere that we studied. In case of SPH simulation, you ought to populate a gas sphere with certain number of particles. These particles represent the gas contents. So when you populate the simulation domain with the number of particles, we call it the SPH particle number. So I followed the simulation with the SPH particle number of 0.25 million. So 0.25 million particles are inside the gas sphere, representing the gas at a specific state. The sphere is of 30 solar masses. This cloud is of 30 solar masses. And the special dimension is that the radius of the sphere is 0.16 parsec. And then the initial density of this cloud is 10 to minus 19 grams per centimeter cube. This sphere of gas is also rotating, and the rotation parameter beta, which is actually the ratio of the rotational energy to the gravitational potential energy of the system, it is just 1%. So this sphere is rotating also. Then when we perform simulations, we ought to understand, we ought to have the idea that what sort of masses we are actually resolving properly. And when we enter into a realm where we can no longer claim that our fragments are actually representing the true fragmentation. So for this, we consider the resolvable mass in the SPH simulation scheme. What we have followed, the number of SPH particles plays a significant role in terms of defining what minimum mass you can resolve to a 1 solar mass object. An object of this mass is actually resolvable with our simulations. And this is also important, that what are the resolvable length that you can claim that you are resolving properly. So this is called the Jeans length. So this is 0.8 10 to minus 2 astronomical units. With this spatial scale, we are resolving the length scale in our simulations. And whenever these stars are formed, it has some accretion radius as well, within which it starts accreting from the surrounding. So we follow a specific value of accretion radius, that is 1 AU. So what you're observing here is a spherical gas cloud, Jeans unstable, which is going to collapse. And this gas is actually transonic in terms of the turbulence involved. So whenever we reach to, just remember one of the slides that I mentioned in which the thermodynamical evolution was discussed. Initially, the gas is going to collapse in an isothermal phase. But when the density reaches to a specific value, it becomes adiabatic collapse. Now that particular density, we regarded this density as the critical density. And we treat this density, let's say, whenever the density reaches to 10 to minus 10 grams per centimeter cube, the isothermal phase of collapse ends and the adiabatic phase of collapse begins. So whenever the density reaches to this value, our sphere is going to collapse adiabatically. Before that, it is going to collapse isothermal. So whenever you form protostars due to this density, when you reach to this particular value, 10 to minus 10, you actually form the star. By the way, this is not the density at which the transition from isothermal to adiabatic occurs. It is actually the density at which we form the stars. The density at which the transition occurs from isothermal to adiabatic is 10 to minus 13 or 10 to minus 14 grams per centimeter cube, which is 3 to 2 orders of magnitude different than at what we form the protostars. So when the density reaches to this value, we form the protostar. These protostars form, obviously, as I mentioned, that every protostar has a certain accretion radius around, and within which all the material that is falling inside this, it is going to become part of the protostar, and the protostar is going to grow in terms of its mass. Obviously, we perform these simulations with the HPC facility, and that is the Lectraru for us. Here in Chile, we use this facility to perform simulations. So over here, again, the model setup, we consider 5 spheres, each representing a specific temperature, 10, 20, 30, 40, 50 Kelvin. And these temperatures are actually representing the CMB contribution. I mean, if you talk about the 50 Kelvin case, this 50 Kelvin case is representing a sphere of gas influenced by the CMB radiation, which sets the flow temperature. And that sets the minimum gas temperature is actually regulated by CMB, and that CMB assigning the temperature of the gas sphere. So the two extremes are 10 Kelvin and 50 Kelvin. And if you see this table, you find that the temperature, the critical density at which the transition from isothermal to adiabatic occurs, these are the values with respect to each sphere. And each sphere actually represents a specific redshift value as well. So we cover the range from 2.6 to around 17 in terms of the redshift. And these are the values at which we expect that the transition is going to happen from isothermal to adiabatic. And all these values represent the temperature which is actually assigned by the CMB to each sphere. On the right, you can expect that how can you estimate the CMB contribution in terms of the minimum temperature that is available for the star forming gas when it is collapsing. So this is the final outcome of our simulation that we performed. These are the initial density sphere from 10 to 50 Kelvin, each transforming from isothermal to adiabatic phase at particular value of the density. And when we see that the cold gas environment and the most high thermal gas environment, the 10 and the 50 Kelvin, these are the outcomes. By the way, since we need to have a more statistically sound results, we perform our simulations with 2 different seed values. Otherwise, rest of the conditions remain more or less the same. We just use 2 seed values to initialize the model setup. So seed 1 and seed 2, these are the outcomes of these seeds that we followed. So 10 Kelvin is end up with a filamentary structure, with these green dots are representing the protostars that form inside this structure. And this is the most warmest of the core. Again, we find that there are protostars existing. And what you notice is that if the 10 Kelvin gas collapses, it collapses and forms quite a pronounced filamentary structure. And it also gives quite a number of protostars to come into existence. But when you compare the warmest of the cores, it's very, it can be seen that there are very few number of protostars forming, and the filamentary structure is also not very pronounced. So this is the immediate apparent outcome that you can see, that the cold gas, when the CMB regulates the temperature and it assigns the temperature of 10 Kelvin, you expect that this contribution of CMB is responsible for producing filamentary structures which will fragment and form quite a number of protostars. And the CMB, when it assigns the gas temperature around 50 Kelvin, because of the high redshift environment, you expect that fewer number of protostars, very few number of protostars going to happen, and these stars are also happening in not very pronounced filamentary structures. So this is the two fundamental outcome that we observe in our simulations. And also, if you are interested how we actually follow the thermodynamics in our simulations, we actually follow the equation of state called the barotropic equation of state. It's a makeshift arrangement. What we do is we do not solve the energy equation. We actually follow the barotropic equation of state, which is dependent on obviously the sound speed and the critical density value that I already mentioned, the value at which the phase transition from isothermal to adiabatic occurs. And obviously the adiabatic index gamma. So the pressure is going to be controlled with this equation of state we call the barotropic equation of state. And also when we estimate these temperatures, how can we assign these temperatures? We follow the CMB, and for each specific temperature, how can we actually estimate at what value of density the transition from isothermal to adiabatic occurs? We actually follow this equation. This is Umukai 2005, which this study actually followed the continuum emission via dust thermal emission and the compressional heating. The balance between these two has been followed, and they came up with this expression that you can estimate the temperature. From the temperature, you can estimate the critical density at which the phase transition can occur. So we follow these fundamental equations, the pressure equations and this temperature equation, which actually provided us the option to determine the exact value of the critical density where we expect the phase transition for all our simulations models, which are varying in terms of the CMB contributions. Another dense slide. I apologize for that, but it's an important slide to mention. As I mentioned that we follow these equations, and what we found is that there are two very fundamental regimes present in any star forming gas or the pre-stellar cloud. When it collapses, it ought to have these two fundamental regimes. One is called the fragmentation dominated regime, and the other one is called the accretion dominated regime. So what you're observing over here is the outcome of our simulations. We find that on the x-axis you have the Jeans masses, and on the y-axis you have the temperature of the gas which is evolving. So let's consider this particular part of the figure. What I'm trying to explain here is that as the temperature, as the gas density increases because of the collapse, the Jeans mass, which is a function of the density, also is going to change. So the Jeans mass in case of the isothermal phase of collapse is a decreasing, I mean, the density is inversely proportional to this, the Jeans mass in this regime. So as the density increases because of the collapse, you expect that the Jeans mass is going to drop down, which means that more fragments can form, can become a self-gravitating objects. So this Jeans mass is going to drop down in this isothermal phase, and when the gas enters the adiabatic collapse, the Jeans mass is now becoming proportional to the density, which means that now the density increases, it actually raises the Jeans mass as well. So it's very tough for the fragmentation to actually occur and to become the self-gravitating objects in this adiabatic regime. Lots of fragmentation is expected in the isothermal regime, mainly because of this particular expression that we have here. However, if we consider one more aspect, is that there are different temperature values. So from blue to the green curves, each curve represents a specific temperature. These are the models that we followed. For instance, M1 is the 10 Kelvin case, and M5 is the 50 Kelvin case. So these two extreme cases are represented with these curves. So what you find is that in each case, the gene's mass is going to evolve and going to be decreased significantly as the collapse continues. But in each case, what we find is that whenever the adiabatic phase comes, the gene's mass starts switching its trend and it starts increasing. So it's tough to form fragmentation. It's tough to form protostars in the adiabatic phase. And if you see the other part of the figure, which is the right hand side of the figure, we see that the density and the temperature is represented here. The temperature initially remains constant because it's isothermal, and then the density and the temperature starts increasing while the density keeps increasing all the time. So this is the trend we found in our simulations, which is obviously very much expected. So these red and the green shades are actually representing the phases of the gas collapse where this process is going on. I don't know how much time I have left because I think I'm not really consistent in terms of the time allotted. Basma, can you hear me?
Yeah, just a second.
Any idea how much time?
You have 10 minutes.
Oh, 10 minutes.
Yeah.
I should skip some of the slides because there are quite many still left. So, okay, let me proceed further. So what we found is that we perform the simulations and we get some statistics. Well, these green and the blue shades are the data that we obtained with respect to each seed value that we followed. So from M1 to M5A, this is the first seed value, and we found that the gene's mass, the temperature, initial values, they yielded variety of protostars, which after merging can become a final number of protostars. There are certain mean masses, there are certain median masses, minimum masses we have. So all the data is available to be analyzed. And we analyze this data at a specific star formation efficiency value. For instance, when the initial mass of the gas converts, that the 2% of the mass converts into the protostars, we stop our simulations at that moment and we try to analyze the data. And then like from 2% to 5, 10, and 15%, we analyze the data at these stages. So what we find here is that if you talk about the star formation efficiency of around 2%, we find that the stellar masses, the many protostars forming in the gas clouds. Remember, let's start discussing the two extremes, M1 and M5, the green and the blue. So we expect that from the green curve that it should be less in terms of the number of protostars, and the masses should be much higher. So on the x-axis you have the masses, and on the y-axis you have the number of protostars. So when we have the 2% star formation efficiency, we find that the expected trend is actually not there. I mean, the masses are all over the place. For instance, this purple line is actually representing the second most warmest of the cloud, and we expect that less number of stars are going to form, and they should be small they should be more massive in terms of this star's mass. But what we found is that the quite low masses available even for one of the warmest of the cores. So there is hardly any trend over here at the 2% star formation efficiency. But if we go forward in time and we analyze the 5% and the 10% star formation efficiency, we start finding that there is some trend going on, in a sense that let's talk about the very last part when the star formation efficiency reached to 15%. Look at this, the green part is the warmest of the core, They are less in number in terms of the protostars, and they are much on the higher side of the masses. Whereas the red one or the blue one, they are much higher in terms of the number of protostars, and they are forming with even much lower masses. That is what we expect. So, and this is again on the right hand side, you have this second seed value. Otherwise, the trend is there to be observed that due to the CMB contribution, the gas, when collapses at a much higher temperature, uh, it is going to form protostars with much higher masses, and the number of protostars in that case will be fairly low. Whereas if the CMB contributes towards the minimum temperature of the pre-stellar cloud, it is going to affect in a sense that you expect much greater number of protostars to form, and you expect that the masses are also could be much lower as compared to the warmest of the cores. So this trend is available for us in terms of the CMB contribution. So apart from the mass spectrum of all the protostars, we also studied distinctively the binary and the isolated protostars. We again find the trend that uh, the binary is also contributing towards the mass spectrum, and the star formation efficiency 15% is actually uh, quite a significant part is coming from the binary configuration which were forming in our simulations. Isolated stars also form, but binaries are quite significant in number, and they also contribute towards the mass spectrum. Then we also find that the mean masses uh, the mean masses are also following a specific trend. And that is also perhaps one of the most important slides. Let me spend at least a couple of minutes on this particular slide. So in the fragmentation dominated regime, which is the isothermal phase of collapse, we find that the CMB contribution is actually not giving a real trend, because all these curves are almost scattered. You don't have really the trend available. But once the star formation efficiency, which is along the x-axis, reaches to a value of around 5%, we find that beyond this, the CMB contribution is more visible over here. So the immediate conclusion from our simulations is that once you reach to a star formation efficiency high enough, and when I say high enough, I mean more than 5%, you start finding a trend that the CMB is actually regulating the star forming gas and actually dictating the masses of the stars, because the mean masses, the green, remember the green curve is representing the highest, the warmest of the cores or the warmest of the clouds, and the blue and the red one are the coldest of the gas clouds. So the CMB contribution is fairly visible over here in terms of the mean masses, but this is only possible when you reach to a specific star formation efficiency. Precisely speaking, it is 5% and beyond that. So we analyzed our simulations, and we also consider the second seed value, and we find the same trend. So we can conclude that the CMB contribution is actually coming into existence with more pronounced effect in the accretion dominated regime, where the adiabatic phase is going on and the stellar masses are more dependent on what was the initial temperature of the gas cloud, what was the CMB contribution of the gas cloud. Uh, in that sense, we say that the final masses of the stars or the IMF is going to be determined by the CMB contribution. We also analyze the maximum masses, and we find some trend. I would like to skip this slide. And obviously, the number of protostars were also following the similar trend. The accretion and the fragmentation dominant regime follow specific trend. Again, the star formation efficiency of around 5% played a vital role. It is this particular value beyond which certain trends are emerging, and the CMB contribution becomes more visible when we analyze the data. This is the This is the accretion history, the mass accretion history of the star, of the protostar that survived long enough in all of our simulations. Uh, I would like to go into the detail, but due to the short time, I cannot. So this is just to give you the idea that uh, all these all these trends and what you're observing here, uh, these small bumps that you find in the accumulation history, these bumps are actually representing the merger events which are happening among the protostars. And whenever this merger occurs, the accretion, the red curve is the accretion, mass accretion profile, the blue curve is the mass accumulation profile. You immediately find that whenever the bump is there, the mass accretion has an immediate rise. But there are cases in which there is hardly any bumps available. For instance, over here, there's hardly any bumps available, but still you have a very high mass accretion rate going on. This we expect that because of the higher thermal environment available for the mass accretion. If you consider the mass accretion process, it is dependent on the thermal state of the environment. So it is very sensitive to the temperature of the environment. In fact, cubed of the sound speed plays a vital role in terms of defining what could be the mass accretion rates. So in the warmest of the cores, we expect that much higher mass accretion rates is possible. And that's why we expect that the mass accretion rates is higher in the warmest of the cores, and hence they're causing a much massive protostars to form. That's the merger history, and this is the and at the bottom you have the net mass accumulation history in our simulations. Okay, uh, we performed simulations, but obviously we did not take into account all possible aspects that should be. For instance, we haven't considered the variety of the turbulent states that could be possible in the star forming gas. So we just follow the transonic gas. This is something that we need to bring into the model to understand more deeply what's going on in terms of the trends. And our simulations also did not take into account the magnetic field. The magnetic pressure can actually contribute towards the gene's mass. So, and that actually helps the gas to resist against the gravity, and the collapse could be delayed. But in the absence of magnetic field in our simulations, maybe we are observing the protostars forming much earlier than what it should be. So that is also one thing that remains missing and that ought to be considered. And also, our models are not following the radiation feedback from the protostars, and that is very vital. So this is one of the caveats that radiation feedback ought to be considered when we try to model these aspects. And the equation of state that we follow is barotropic. Ideally, it would be nice to actually solve the energy equation rather than following the makeshift arrangement like the barotropic equation of state. And obviously the external radiation sources, we just follow the CMB, but we know that the supernovae and the radiation from the nearby star forming regions can also contribute, and the cosmic rays can also contribute towards the minimum temperature of the pre-stellar gas clouds. All these aspects remain uh, missing. So we believe that whatever we have observed in terms of the trends, maybe these trends can be further refined if we consider all these aspects into our models as well. Uh, this is the conclusion. I left with this slide, and I stop here, and I welcome if there are any questions. Thanks.
Okay, thank you. Any questions?
Well, here's Roberto Saglia. Can I ask something?
Yes, please.
This is the second talk we heard in the last couple of weeks, month, about star formation, and I will ask you the same question I asked last time. You are telling us that the number of low mass stars is low if the cosmic background temperature is high. But what we see at the centers of elliptical galaxies that are old and must have formed the stars long time ago when the CMB temperature was high, we see that the IMF is super salpita. So there are lots of small stars that must have formed at high redshifts. And this is puzzling.
Yeah, you're right. But what I mentioned in one of my slides is that you can expect the low mass stars even at much higher redshift environments as well. And there are mechanisms available that actually can trigger the low mass stars, which eventually, when they start accreting, the high temperature environment helps the accretion process as well. So the accretion itself is fairly sensitive to the temperature available in the environment. So in the high redshift environment, if you find a very high star formation, or rather the high mass stars are there, it is mainly because the high accretion rates was available for the stars to actually grow in mass and end up with a much higher masses. But you're right, the IMF actually deals with the stars with which you form the cluster. It is puzzling. I would say that high mass stars, it could be the final state of the population, but a newborn population, we should expect that the high mass stars should not be very high in number.
So let me throw in another ingredient that you might not have put into your simulations yet. Elliptical galaxies are also the host of most massive, supermassive black holes. And they are active at high redshifts. So could it be that it is the supermassive black holes that somehow destroy the high mass stars such that only the small ones can stay there?
Yeah, this could be one of the possibilities, that the radiation or the effect from the supermassive black holes can actually affect the high mass stars, and just the low mass stars can remain there. But you rightly mentioned that there are a lot of ingredients that remain missing in my simulations. This is just the CMB based contribution, which is just giving us the trend. And you rightly pointed out that there are certain things that ought to be considered when we try to understand the IMF and the universality of the IMF. That is very important.
Any other questions?